I'm Mirko Bracale, first year SPIN PhD at ISTerre in Grenoble. And today I will talk about a study that we did in the first months of my PhD. In which, okay, can you hear me? Okay. In which we investigated the effect of shallow heterogeneities on wavefield gradient measurements. So the first question, so we try to answer to the question, how sensitive are the wavefield gradients to shallow localized velocity changes? In order to answer to this question, we structured our work in this way. So firstly, we modified the spectral element simulation software to observe as a direct output the rotations and the strain in addition to the displacement. And then we performed many experiments, simulations, by using a seismic array placed above a velocity anomaly. And then we consider two kinds of anomalies, a weak anomalies, where the velocity was dropping by 10% compared with the homogeneous medium, and a strong anomaly where the velocity was decreasing by 70%. So the first question we should answer is how a seismic anomaly interacts with the wavefield and is observable. So what we can study about the interaction with the heterogeneity and the wavefield. So we performed each experiment 2 times, one considering a fully homogeneous medium, and then placing the seismic anomaly inside the medium. And what we can study are 2 things. So the phase shift, that means that the seismic phases can acquire a delay or an advance with respect to the homogeneous case, and or the amplitude variation. That means that we can, the normalized waveform can change its amplitude when the anomaly is placed in the medium. So since we will work on noise velocity monitoring, we focused on the phase shift. And we have a really precise method to measure the phase shift by frequency time decomposition, which is the wavelet transform. So here we can see the settings of the main experiment that we did. So on the left, we can see the configuration, the source, the seismic array, and the elliptical anomaly, which was beneath the seismic array, where the velocity drops by 10%. Then for each one of the receiver, we compute the cross wavelet transform that allow us to estimate the delay for as a function of the frequency and of the time. And we focused on the railway. So we have been able to measure the delay of the railway in different range of frequencies between 1 and 15 hertz. So for each one of the receiver, we obtain these values. And so here we show basically a comparison between the delay that we observed looking at the displacement and looking at the wavefield gradient. So up we can see the displacement versus the strain, and under the displacement versus the rotation. What we see is that there is a frequency dependence of the time delay, but this is expected because we are looking at rail waves, so we know that the sensitivity kernels are function also of the frequency, and due to the settings of this experiment, we are expecting the maximum delay between 3 and 4 hertz. That is what we see. But what we want to show mainly here is that if we look at the different observables, we do not see any significant difference in terms of time delay if we look at the wavefield or at its gradients. And this is also shown here, in which we basically here we have a plot in which each number identifies a receiver of the array, and we have the displacement and the rotation on the right. The data refers to the range frequency between 3 and 4 hertz. And what we see here is that the delay is the same. There are fluctuations of plus minus 1, but these are related to the computational error. So this is not enough for us to say that there is a significant difference in terms of sensitivity if we look at the time delay. We also did another experiment in which we used a really strong velocity anomaly. So this is the configuration. The velocity was dropping by 70% inside the seismic anomaly. Now, due to the really strong impedance contrast, we saw some reflection of S waves inside the anomaly, and this perturbed our waveform. So if the waveforms are too different from the homogeneous case, then we are not able anymore to use the wavelet transform to analyze the delay. So we have not been able to use the wavelet transform in this case, and so to study the phase shift, let's say. And so we studied the amplitude in this case. And if we look at the amplitude, what we see here is that actually for the receivers which are exactly above the anomaly, we do see an amplification. Here there is a comparison between the vertical velocity and the rotation along the y-axis. And what we see here is that if we look at the receivers exactly above the anomaly, we see an amplification of the rotation, as is also described in other papers. So in conclusion, let's say if we look at the weak anomaly, and here just I would like to say something, because we call the weak anomaly an anomaly where the velocity was dropping by 10%, but this is in terms of seismic velocity monitoring is not at all a weak anomaly. We are expecting to see some fluctuation of 0.something% or some percent of velocity. So for the purpose related to seismic velocity monitoring, moderate change up to 10% of velocity, the wavefield gradients do not show an increased sensitivity compared with the traditional observables. But when we looked at the strong anomaly experiment, we saw that the phase measurements are not effective because the waveforms are too different. We do see a local amplification of the gradients, and maybe this larger sensitivity in terms of amplitude could be used for in the future for a full waveform inversion purposes. And that's all for the moment.